Okay, hello everyone. I'd like to get started. The first thing I'd like to point out is on the class schedule. Um, until 2 minutes ago, there was nothing for this lecture. Now there is something for this lecture. So you can go here. It has the code link here. And this time I'm not going to be going through slides. I'm going to be going through like demonstrating some stuff in a Jupyter notebook. So there's no slides link for today, but you can click through and run it yourself. Um, the reason why I want to do this is I want to show like a very minimal example of some of the like algorithms that we're going to be using this time to set everything up so that you can use it properly. Um, so oh yeah, and actually before that, let me do some logistics announcements, which is number one, starting next week, we will have office hours. The TAs and I are arranging everything, but that will be posted on Piazza. All of the class videos will try to post on Piazza as soon as we can. The homework is not out yet, but it will, homework one will be out soon. Any other questions that people had about general logistics things? Or are we all set? Okay, cool. So let me go ahead with this. And so some of this may be relatively elementary to everyone, but to some people. But one thing I've noticed is that actually a lot of these concepts are not, as universally held as I may originally thought. So I just want to make sure that we get everybody on the same page. And so today is in four parts. The first thing I want to talk about is some probability fundamentals. And these are going to go into like basically everything we do. So we'll talk about that first. The second thing I'm going to do is just going to show a very basic implementation of a transformer model. Again, I assume that most people have dealt with this before, but this implementation may also be useful if you want to try it out in future work. So I'll just go through it quickly. And then after that, I want to show some generation algorithms and how we can evaluate models using language models as a judge. And then finally, I want to talk a little bit about meta generation algorithms, which are like re-ranking algorithms that allow you to pick the best output. And not everything's in the code. I'm going to go off track a little bit some of the time, and also please feel free to ask any questions. So yeah, let's get started. So the first thing that I want to talk about is probability fundamentals. And so I'm going to go through some basic concepts, and I would definitely encourage you to go walk along with the code. You can run it locally. If you click open in Colab, you can run it on Colab, but you'll have to like copy paste in the library files, so it might not be super convenient. The first thing we do is just set up our environment with Torch and NumPy and Matplotlib and import everything. So this is not interesting. Um, so the first thing I want to talk about is conditional probabilities. And the reason why I want to talk about conditional probabilities is because we are dealing with autoregressive language models mostly, and autoregressive language models are based on conditional probabilities where we predict the probability of the next token. Have people learned of any variety of language models other than transformers? Yes?
Okay. Word embeddings.
Word embeddings. So that's a good point. Is a word embedding a language model, according to our definition last week? Anyone remember what the definition of a language model last week was? It's not a trick question, yeah.
Right, essentially predict one specific token given like the previous tokens that you already put.
Yeah, model that predicts the next token given the previous token. Yes, that's specifically an autoregressive language model. So if we go even broader, it's a model that, yeah.
Generates text.
That generates text. Yes, it should have the ability to generate text. That's actually not how I defined it on Tuesday, though. Yeah.
Does it generate sequences of tokens?
Sequences of tokens. Yes, but that's also not how I defined it last Tuesday.
Assigning probabilities to sequences.
Yeah, assigning probabilities to sequences. So, and then specifically, autoregressive models assign probabilities to sequences by predicting the next token. And so when we predict the next token, that's a conditional probability. It's the probability of the next token given all of the previous tokens. Or the probability of y given x, where x is the previous tokens. So now going back to the question, is Word2Vec a language model? If so, yes. If not, why not? Any ideas? Who knows Word2Vec, by the way? Maybe not everybody. It's yeah.
It isn't inherently assigning probabilities, it's a definite generation of like embeddings.
Yeah, so Word2Vec, for people who aren't familiar, I can draw it quickly on the board. Basically, it's a way of learning embeddings for tokens, but what it does is Word2Vec's actually a software toolkit. It's not any individual method. It's either of two methods where basically based on the surrounding tokens, you're predicting the tokens in the center, or based on the token in the center, you're predicting the surrounding tokens, and then you use that to learn embeddings. But this actually violates the principle of going from left to right, and so it can't be an autoregressive model. And if you work really, really hard, you can kind of turn it into a language model that actually predicts the probability of sequences, but it's like not designed for that purpose. So any other ideas? BERT is also similar, by the way. BERT is it's called a masked language model, but it's actually really hard to get it to assign a probability to sequences. Any others? Yeah. Diffusion models. Yes, very good. But that's not the one I'm looking for. Recurrent neural networks. Yeah, that's a very good one. Did anyone take a kind of old school NLP class? What did you learn as language models there? BM25. BM25 is more of a weighting thing. Yeah. N-gram models. Yeah, there we go. So N-gram models are maybe not taught so widely anymore, but they're a good illustrative model that we can work with. An N-gram model, basically what it is it predicts the next word based on the previous n-1 words. And in this particular case, I set up a bigram model, which is a 2-gram. So it predicts the next word based on the previous one word, the next word based on the previous one word. So I came up with a fake n-gram model where I just kind of assigned probabilities to this very small vocab of beginning of sentence, the cat, dog, park, mat, sat, ran, walked, played, on, in, to, quickly, slowly, and end of sentence symbol. And I, or more accurately, Claude, came up with these probabilities for each of the tokens here. So, given the beginning of the sentence, what is the next possible word? Like the cat, dog, park. Given what is the next possible word? Cat, dog, park, et cetera, et cetera. And so this definitely satisfies this equation here, but it also additionally, who mentioned the Markov assumption last time? Yeah. So this has a Markov assumption, which means that we are only paying attention to a certain number of previous words, and so we're basically lopping off everything except the immediately previous word and just ignoring it and only conditioning on the previous word. So what this gives us is this gives us a set of conditional probabilities that look a bit like this. And so given S, given the previous word was S, we can predict any of these words. Given that the previous word was the, we can predict any of these words, any of these nouns. Given that the previous word was cat, we could predict things like sat, ran, walked, played, et cetera, et cetera. So we're not actually going to use any of these models. I'm just using them here because they're very fast to calculate and easy for illustrative purposes. But there we are. Any questions, Sarah? Who's actually like implemented or used an n-gram model in a class? Wow, I feel 2025. That's exciting to see the change. This was like the staple 5 years ago, I think. So, cool. Okay. So now I want to talk about sampling from language models. So this is the most simple inference algorithm that we're going to use. It's also a very special inference algorithm, which I'm going to talk about in a second. And so basically the way we sample from a language model is we start from the beginning token and use the conditional probabilities to sample the next word, update the current context, and repeat. And then we continue until we reach an end token or maximum length. And so this is like what we do in every autoregressive language model. It's the same for transformers. The only difference is here, for updating the current context, we're just remembering the previous word. In a transformer model, we run it through many, many layers of the transformer model and like append the embeddings to the KV cache and all of the other things. So, but the overall way of implementing this is the same. So, what we do is we take our vocabulary, we get a list of all of the keys in the vocabulary. And we start our sequence with just the beginning of a sentence. So set that as our current index. And then we step through until we get to a max length. And actually, this max length is important when you're using, any sort of like neural network or deep learning based language model, because it may go on forever if you're not careful. So you kind of need to set this so you don't run out of memory. So I'll get to temperature, or no, I'll explain temperature now. So we're going to talk about a lot of different sampling algorithms. Temperature sampling is a very common one that we use. And basically, the idea behind temperature sampling is that we might want to make the distribution more peaky or less peaky so that we get more higher probability outputs or lower probability outputs. And so in a mathematical equation, what we do is we take the probability of I. And so typically, if we have a probability, all of these will add up to 1 because it's a probability and probabilities need to add up to 1. And so this sum is just 1, so we don't need to worry about it. So the probability of I is the probability of I, right? So typically we could just cancel this out. But what we do when we have a temperature is we make an adjustment where we take E to the log probability of I, E to the log probability of J. And then we multiply it by 1 divided by the temperature. And so what does this mean when the temperature is 1? Any ideas? Yeah, nothing happens. It's a no-op because you get 1/1, this is 1, and then E and log cancel out, and we get the same thing we had before. What does this mean when we set the temperature to be infinity? All of the values will become one. And so what that means is, what if our vocabulary size is 1,000? Yeah, each of them will have 1 by 1,000. So it gives us a uniform probability distribution. What if we set this to 0? For the probability? It might be undefined at infinity, but what's the limit as it approaches infinity? There's only one single probable word. So basically what happens is the largest token becomes infinitely larger than all of the other tokens. Because because it's multiplied and then exponentiated. So basically, like what that means is you get a one-hot vector, where a single word, actually I'm mixing word and token, but let's just say token, where a single token gets a probability of 1 and all of the other ones get a probability of 0. So you'll always pick the most probable token. Slight caveat, if 2 tokens have exactly the same probability, then you would get a uniform distribution over all of the most probable tokens, but basically it is you pick the most probable token. So that's what we're doing here. We're basically taking the log of the probabilities, we're dividing it by the temperature, and then we're taking the softmax, and the softmax is basically exponentiating and then normalizing. So that's what we do here. So once we've done this, we then sample the next token. So if we're not taking the temperature, we sample it according to the original probability distribution. If we do take the temperature, we sample it according to the adjusted probability distribution. We append this as the next word to the sequence, and we continue until we hit the end of sequence token. Okay, great. So let's try it out. I'm just sampling some outputs from the model. And my model gave us the dog played, the cat played quickly, the dog played in the park walked. So I don't know if anybody's heard of a garden path sentence, but this feels like a garden path sentence here. It's one of those sentences that kind of seems to make sense until you hear the last word, and then it doesn't make any sense at all. But basically, the reason why we use big transformers is because bigram models like this are really bad models of language, so they give you lots of like very unnatural things. But anyway, like this is, we can generate something that vaguely looks like English in this way. So anyway, we're not going to use this model. We're not going to use this model to do anything. It's mainly for demonstration purposes. And the next demonstration that I would like to make is how we estimate quantities through sampling. And the basic idea is here we have a true conditional probability of the next word given the current word. So we know this according to our bigram model. But what if I said I wanted the joint probability of 2 words co-occurring here? And so the joint probability would be not not the conditional probability where we divide it by p of x, but just the thing on top of this. So just like what's the probability that these 2 words, if you looked at any 2 arbitrary words, that the first word would be x and the next word. So does anyone have a good way to calculate this? Like, could you write a program that like solves for this value by taking in this big matrix? Yeah.
What is the probability of not operating and what is the probability of both those not operating together?
The probability of both words not occurring together. Yeah, I mean, if you could get that, you could get, you could maybe use that to find this. But basically, long story short, coming up with an analytical solution to this is maybe possible, but it's hard. Like it's not very easy to take these conditional probabilities and come up with a system of equations that would allow you to come up with this joint probability. And it becomes even more impossible when you start talking about like finding this joint probability for a transformer-based model. You just wouldn't be able to do it, right? So what we do instead is we can actually estimate quantities through sampling. And so what we can do is we can generate a whole bunch of sentences with the model using our sampling algorithm and estimate this estimate this unknown quantity, this joint probability of the two. So why is this useful? This is useful for a very large number of reasons. It can be useful for example, let's say you have a transformer-based model where you can calculate conditional probabilities, and you want to know what percentage of the time it generates toxic content. So there's no analytical solution where you throw in your, transformer and like say, okay, now run the system of equations and tell me how much toxic content there is. But what you can do is you can sample a million outputs and see what percentage of them are toxic. And so that gives you the expected number of like toxic outputs that it would generate given a particular prompt or something like this. But we're gonna do something a little bit more boring, which is just estimating the joint probability of any two tokens in a sequence. And so what we have here is we have our bigram count. We have the total bigrams. We sample a certain number of sequences. And based on this, we find the current index and the next index, and we just add to the bigram count and the total number of bigrams. And then when we're done, we divide the bigram counts by the total number of bigrams. And that gives us the joint probability of having these two in a sequence. And so let's run that. I also have a function to estimate conditional probabilities from sequences, but this is a little bit like uninteresting at this point because we already know the conditional probabilities. So why do we need to, estimate them from sequences? So we'll do that later. So what I want to do now. Oh, actually, sorry, no, I am going to demonstrate that we're going to estimate conditional probabilities from sequences. And the reason why is because the more we sample, the better our estimates become. And so if we sample more and more outputs, our estimates are going to become more and more accurate. And I want to demonstrate this by looking at the conditional probabilities that we estimate by counting up all of the bigrams and then dividing by the number of times we saw a previous word and comparing that with the true conditional probabilities that we know because we know this is a bigram model. So yeah, sorry, actually maybe just to rewind a little bit. The way we can estimate a conditional probability from a sequence is we look at the current ID, we look at the next ID, we calculate the bigram count, we calculate the count of the first word in that bigram, and then we can calculate the conditional probability by dividing the bigram count with the current word count. So basically calculate this without the like X in the bottom. So let's do this. And we're going to calculate the bigram counts or the conditional probabilities for cat given the, sat given cat, the given on, and on given sat. And I won't go through like all of this code here because it's a little bit involved, but let's run this. And what we can see is if we sample 100 outputs, the actual conditional probability of on given the is 0.5, and we happen to get it like exactly right when we sampled only 100 outputs. But all of the other ones, we actually got zero. We got 0% probability for like sat given on, for instance. So basically, if we only sampled 100 examples, we got a really bad estimate of many of these. But then if we scaled up to like 500 or 1,000 or 5,000, 10,000, 50,000, sorry, wait, 100, or sorry, 10, 50, 100, 500, 1,000, 5,000, and 10,000. We can see that gradually, like our estimates are converging to the actual value that we know is correct. And so like the more we sample, the better estimates we get. And this is like looking at all of the outputs, how much does our error converge after we sample that many times? Yeah.
This somehow,
Great question. So the question was, does this somehow depend on the temperature? Does anyone have an idea about whether this depends on the temperature? I'm going to show you a plot, but yeah.
actually just modifies.
Yeah, it does. And the answer is it depends on the temperature because the temperature modifies the probability. So yes, that's absolutely correct. And the actual answer is 1 is a very special temperature. It's the only temperature that gives you the true probability distribution. And it's actually the only temperature where you can where you can accurately sample from the joint distribution according to that temperature, all kinds of other things. So if you sample with a probability of 1, you're actually guaranteed to get an unbiased if you sample from the conditional probability, or sorry, from the joint probability distribution that you can get from the conditional probability distribution. So I don't have the autoregressive equation up here, but basically like if you multiply all of these together, you get the joint distribution of all of the tokens of the sequence, right? So yeah, if you don't use one, you get it incorrect. Cool. And then these are the final estimated conditional probabilities. We'd have to scroll up to compare them to the real conditional probabilities. But like as you sample more, you're going to get this closer and closer to the actual distribution. So this is important for a number of reasons. Any questions here? This is also important for model training. Anyone know why this is important for model training? Any ideas? Yeah.
Prevent like evil contents.
Prevent evil contents. It's not the answer I was looking for, but maybe. Yeah.
Yes. This basically that, like we use also answer is what the true power distribution is, the better. But that's something.
Yeah, so basically, if we want to, so the answer was if we want to match the true probability distribution of like text on the internet, we just need to sample an infinite amount of text on the internet, and we'll get a unbiased sample of of the text. I mean, what does unbiased mean here? Depending on what sites you download and stuff like that, you might not be able to get like all of the words that people have ever said, but you can get pretty close with the internet. But the other implication is if you have a small sample, it's not going to be able to give you a good estimate of what all the text on the internet looks like. So when you train on only a small sample of data, you're going to risk overfitting and other stuff like that. So it all boils down to basically this. So yeah, so then the next thing I want to talk about is marginalization, which is summing over variables. And this is also important, and we're going to be talking about it a lot in our meta generation section. But so can somebody, I kind of actually already said the answer. So marginalization is basically taking this sum, for example, taking the sum over y and predicting the probability of x, or taking the sum over x and predicting the probability of y. Does anyone know why it's called marginalization, by the way? Anyone heard of this before? Yeah. Yeah, exactly. You write the sum in the margin of the table. So what if this is a table of all of the probabilities? Actually, this is a conditional probability, so it's not as interesting. But if you have the table of the joint probabilities, you would write the sum in the margin over here because it would be the sum of all of the like values in the row or all of the values in the column. So that's where the word came from. Great. Okay. So the way we do this is not that tricky. Basically, in PyTorch, it's a single call. We just sum over the dimension, like dimension 1 or dimension 0. And we estimated the joint probabilities from the sequence. So we're going to base this on the joint probabilities. And actually, I have the joint probabilities here. And you can see that the marginal probability of this being the current word is this. So the highest probability current word is the start of sentence symbol. The start of sentence symbol can never be the next word, so its probability is 0. And then we have like different values. And we got all of this without me not, ever being able to calculate this directly or analytically, because we can sample and we can calculate these things. Okay, so in particular, why I wanted to talk about marginalization is I want to talk about latent. Yeah, sorry. Sure.
In this chart, like as we increase the number of sequences, do we see that it plateaus after a point of time, given that, I mean, we have scraped like, say, just 100,000 sequences or something. Do we see the error convergence that we
So this should go to 0. Like if you sample infinitely, because we're sampling in an unbiased manner and we're just calculating counts. So this error should go to 0 if I do more. Like you wanna try. Let's make my laptop a little bit hotter. I might need to change. Okay. Maybe this will just work. My sampling is also not optimized. I am using very inefficient inference algorithms of Python for loops. So this I would suggest you use an optimized implementation if you try this. Actually try this. So yeah, well, while that's working, maybe I will go on to the next part. So latent variables. So this is hidden structure. Like hidden variables that are not maybe necessarily the input that you have or the output that you care about, but somehow have an effect on the final output. So you like to include them. So there's a really common variety of latent variable that we use in language models nowadays. Anybody have an idea of what this might be off the top of your head? And this needs to be a probabilistic variable, so it's not like the hidden embeddings or something like that. It's very, very popular as of about 12 months ago or 9 months ago. What's a big trend in language models nowadays?
Is it reasoning?
Yes, reasoning. So recently, a big trend in language models is reasoning models. And basically what reasoning models do is they have a chain of thought or a long chain of thought that they use before giving you the final answer with the hope that adding this chain of thought will improve the overall quality of the final answer. And so here, X is the first word, X would be like your input prompt. Z would be the reasoning trace of a reasoning model, and Y would be the final answer that you would be providing. And so that's one example. There are other examples, but this is definitely the most prominent example nowadays. And so the idea is if you calculate So let's say we have a model that has no chain of thought or no reasoning whatsoever. It would be calculating the just the conditional probability of the answer. A model with chain of thought might generate the chain of thought and then generate the answer. So this is calculating the joint probability of the chain of thought and then the answer. And let's say we don't care about the chain of thought and we just throw it away, but we can actually sample lots and lots of them. So this is a method called self-consistency that's used pretty widely. And we're also going to talk about minimum base risk, which is kind of similar to self-consistency in a way. And what that means is you do so you sample the chain of thought and you and actually like I could have just used that as well. And then you sum over all of the samples that you got. And this gives you an estimate of P of y given X. And or it's an estimate of P of y given X. And this this is similar to predicting directly, but because the probability of y gets more accurate by adding this reasoning, you actually get a better estimate and you get better results when you do this. So we're going to talk a lot more about this, but this is like the connection to modern language models. But here I'm going to focus on kind of the like I'm just focusing on like the basic idea of this. And actually, this just finished. It's not converging as fast as I thought it would be, but you can see it definitely went down from where it was before. So yeah, I'm almost a little bit worried I have a bug in my code, so I need to go back and double check that. But this should eventually approach 0. Yeah. So yeah, and so like in this particular example, we could generate and we could say the first word is X, the last word is Y, and then all the words in the middle are the latent variables. So that's kind of like what we do with chain of thought. Just in the interest of finishing everything. So just to go back to the point about temperature and biased estimates. So this is what temperature sampling looks like. And so like let's run with temperature sampling, the same experiment that I ran before. And basically what we can see is that if we sample from a model where temperature is 1, this gives us an unbiased estimate of what the actual conditional probabilities are. And so our error goes down and down and down and down. But if we're sampling from a biased estimate of what the probability is, then this indeed will plateau, and this will not give us a correct estimate of what the output of the model will look like. So why is this important? This is important because almost nobody does this, this temperature sampling of 1. Like some language models enforce it. Like I think O1, like the OpenAI reasoning models enforce temperature of 1, and you're not allowed to do other temperatures. But a lot of models, for various reasons, which I'm going to talk about in a second, use like use this. And actually, if we go even more extreme and we say we're going to set the temperature to 0, we're going to do greedy. We're going to do this greedy. Let's see. But my code was not robust to sample from from zero. But like if you did greedy, it would be even more biased. So like what this means is unless we're sampling with a temperature of 1, we're not getting like the actual language model's like model of language, right? We're getting something that's like a bias distribution that the model isn't actually generating. Cool. So like let's say then the question is like, why do we want to do inference? We actually had a question about this last time, but one reason why we might want to do inference is to get good outputs, in which case, we want to use any inference algorithm that will give us the best outputs by whatever definition of good we have. The other reason could be we actually want to understand the qualities of the language model, and if we do, then basically sampling with the temperature of 1 is the only way to get the true distribution of the model. So that's a good thing to remember. Okay, that's the first part. Are there any questions about that? Yeah.
There any use case where we said like that's online or done with arbitrary?
Is there any use case where you set the temperature to greater than 1? I have almost never seen this. I've seen this like a little bit, but almost never. And actually, I think you might see the reason why in the slide or in the notebook after the one that I'm going to talk about. But usually 1 is kind of the upper limit of what people said. Yeah.
Temperature of 1 gives an unbiased estimate. Why are we using the temperature distance? With 1, it means 0.
Yeah, that's great. Why don't I show the next notebook and then get there? Cool. So I actually don't know if I'll really go through this. I'm kind of assuming, everybody has either taken NLP or deep learning or something. So this is just a transformer model. The nice thing about this transformer model is that it's very, very simple. There's like 2,000 lines of code in the Hugging Face Transformers implementation of GPT-2, and this one has like a couple hundred. Yeah, it's basically the GPT-2 model. The few things that I think would be like particularly interesting to take a look at are how big is this model? So GPT-2 small, basically it had a vocab of 5,000. It had 12 layers, 12 heads, and an embedding size of 768. This had 24 layers, 16 heads, embedding size of 1024. And then large had 36 layers, 20 heads, embedding size of 1280. So this is approximately like 10x smaller than the models that we use nowadays for most of these dimensions. Except maybe layers, the size here is. Cool. So let's go on to the generation part. And so here in the generation, what I want to do is I want to do 2 things. I want to get like a qualitative idea of what the output looks like when we sample at different temperatures to answer like some of the questions that we just had now. And then separately from that, I want to demonstrate how we can do like some very rudimentary evaluation. And this is not like, the gold standard way of doing evaluation of language model outputs, but it'll give you an idea and like a starting place where you can start until we get to the gold standard ways. So here are temperature values. So 0 is greedy sampling. It's deterministic. It should always give you the same result. A temperature of 0.5 is kind of a more conservative variety of sampling, and it will focus on things that kind of have high probabilities. 1 is, the only true sampling number, and then 1.5 is creative sampling, more diverse outputs. So let's go ahead and initialize that. One thing I will notice is I kind of cheated here, and I'm using an API key. So I'm like actually asking Claude to evaluate my results for me, but all the generations are going to be from my model. Oh, and by the way, I'm going to try to get everybody, number one, I'm going to try to get everybody like credits that you can use on API-based language models. Everybody will get $50, so it's not a lot, but it should be enough for like these language model as a judge sale things. And we want everybody to sign up for AWS if you haven't already with your Andrew ID and tell us your AWS number. And we have a quiz that you created already.
It was, it'll be with the one today.
Okay, the quiz will be with the one today, so please try to add your number there, and I'll try to get you AWS credits as soon as possible. But back to the normally scheduled programming, I'll do temperature sampling, and this time we're doing it with GPT-2, so it'll give us like actual like somewhat reasonable looking results. Oh, one small thing that I probably should mention. Is within this. Oh, actually, maybe it's not here. But if you're using a Mac, I would definitely recommend that you use the Mac accelerator. I think like most people have Macs here, and if you have Apple Silicon, it makes it a lot faster. So there's an example of that in this notebook. Cool. So here are the texts, and I'm going to generate, based on a prompt, the future of artificial intelligence is, and I'm generating 3 from each of these outputs. So basically doing inference 3 times for each. So if we look at greedy here, it gives us the same answer always. And it says, the future of artificial intelligence is uncertain, period. We're not sure what the future will look like, said Dr. Michael S. Schoenfeld, who I don't know if that's a real person or not, but given, I think it might be, given that this is greedy decoding and it's probably not going to be too creative, but yeah. Then for this one down here, oh, actually, one piece of knowledge about greedy decoding that I should say here before it drives you crazy is when you do greedy decoding, will you always get the same result? I got the same result 3 times. Yes? Yeah, no, sorry. You will not always get the same result. And there's a reason for it. Does anyone know the reason for why you might call like GPT-4o or Claude or something like that with a temperature of 0 and get different results? This is a kind of yeah.
Okay, so you sampling for the probability then yeah.
Because you're still sampling for the probabilities and not the actual values. What do you mean by the probabilities?
Which to open should for the next year not decide that they do some.
We said so. Actually, when you switch it to 0, it's mostly just picking the highest scoring ones. So specifically in the case of 0, you'll be picking the argmax. Yeah. Floating point errors can propagate. Yes. So this is very, 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 very tricky, but it has to do with the hardware that all of these models are running on. And basically all of these models are running on GPUs. And what's the characteristic of GPUs? They have lots of threads, right? That are all running at the same time. And so there's 2 ways you can do a sum on a GPU. One way you can do a sum is you say, okay, thread 1, let's say we have 16 threads. Thread 1, you calculated 1, so you get to go first. Thread 2, you calculated 2, so you get to go first. Thread 3, you calculated 3, so you get to go first. And then you just add them all in order. But the problem is if you do this, you have a whole lot of locks, and like some threads might finish a little bit faster than others just due to how hot the GPU was or whether it had a good day yesterday or things like this. And so if you add all of these locks, it hurts your efficiency a whole lot. So theoretically, you could turn on determinism on GPUs and make things go all in order, but in reality, none of the people serving things on GPUs does this. So what happens instead is thread 7 finishes a little bit faster. So thread 7 gets to go first, and then thread 2 finishes. And so thread 2 gets to go next, and then thread 1 finishes, and then thread 3 finishes. And so the addition happens in a different order every time, just based on like, well, nothing is random, but mostly random factors. And so because of this, if you combine this with the fact that the very small floating point numbers, depending on the order you add them, will round differently, this can cause very small differences when you run. And so these differences are really, really tiny. But you have something like an argmax when you select the vocabulary item. So if the maximum vocabulary item changes just once in your like 1000 token generated sequence, then it will change everything that happened after that. So you only need a very tiny difference caused by these floating point errors to throw things off. And so you'll notice if you run like something with Claude, you'll get it the same like 5 times, but then you'll get it different once or something like this. This is compounded further by 2 things. The first thing is mixture of experts. And so mixture of experts are a very popular thing. We'll talk about them a little bit, but basically you're choosing which parts of the network to use. So now instead of having an argmax over just the token, you also have an argmax over the experts. So you have like many, many more argmaxes. And then let's say you're running an agent or something like that, like a coding agent. Now you don't just have one prediction, you have many, many predictions. So like when we were trying to reproduce our coding agent results with Claude, we would never be able to get the same results on the same, even on the same instance with like greedy sampling. Yeah.
I'm wondering if because there's still this randomness, even though it's very small, whether or not that corresponds to what temperature exactly would like empirically, whether or not it's set to 0, but because of these hardware quirks, it's actually more closer to like a number than 0.01 or something. If anyone that has ever tried to measure that.
That's a great idea. Just to repeat, it's like, what is the empirical temperature? Despite the fact that your set temperature is 0, what's the actual temperature that you're getting? And I don't know the answer. Yeah.
Forget, by also using multiple instances of GPUs.
Does it get compounded by using multiple instances of GPUs? Yeah, it depends where you aggregate, but like if, you know, one GPU is more likely to have a larger difference than the threads within the GPU, so it certainly would. Yeah.
You should make this problem.
Does quantization make the problem worse? Yeah, it will, because you'll have more rounding errors.
Can you use this behavior to kind of infer like what kind of forms the model is made?
Can you use this behavior to infer what kind of quantization it's using? So basically you want to like uncover what quantization OpenAI is using or something like that. Good idea. Please do that. I'll give you an A+ on the project if you can demonstrate that. Or prove that. I'll give a high bar, but cool. Okay, so now let's go to the temperature 0.5. So the future of artificial intelligence is in question if you're a software developer and you are looking for a new way to create and deploy applications. Clear, and the future of the world is bright. The future is bright. The future is bright. Very bright. It's a lot like the future of computers. I'm not sure what the word intelligence. And then for one, you have like largely up in the air, many eagerly await and think, seen Jokawi's creation. They expect to see everyone around be clear. Automaton 2017, the future of artificial intelligence is clear. Facebook just topped out. Going to be very interesting. It will change the way we think and treat people. The future of artificial, and then going up above temperature of 1, the future of artificial intelligence clashing across the league allies and designer gangs. Circuit feared the waddling bastard Bengal error. So maybe this is kind of your answer why we don't use a temperature larger than 1. It just kind of goes off the rails. So So then the question is, we looked at this and we kind of like had an idea what was going on here from our, own qualitative analysis, but we can't do this all the time, right? Like I couldn't do this very well in Chinese for sure. Uh, and I couldn't look at thousands of examples. And so you can run this. And so what I want to do next is I want to actually like evaluate the outputs and see how good they are. And there's a number of ways to do this, like I mentioned before on Tuesday. So the first way you can do this is you can use some sort of deterministic metrics that you can calculate, directly from the generated text. And for this, I'm going to use a diversity metric. And so the diversity metric is that I'm going to use here is the ratio of unique words in the set compared to the total number of words. So sorry, this is the diversity within a single example. And then for the cross-generation diversity, what I'm going to try to do is find the overlap of words or bigrams between the two outputs. And if there's less overlap, then it will be more diverse. So these are kind of like, this is just an example of a deterministic metric you could do. You could also measure the length. You could measure, other varieties of things like this. But another popular way of evaluating things is using a language model as a judge. And so the reason why this is nice is it's like super easy to do super powerful things with this by just asking a language model a question about the output. There's a lot of caveats that go into this, which I can talk about a little bit, but here I'm just going to show a very simple example, which is rate the fluency and coherence of this text on a scale of 0 to 10. 10 equals perfect, only respond with a number. So I'll do this, I'll give it my API key, and then generate. Cool. And then to run the evaluation, I'll take all the things that I generated before and run them to calculate this fluency score and the evaluation score. So it's evaluating each of these. I didn't, for the purpose of simplicity, I didn't speed up my LM calls. Like in reality, if I did this, I'd use kind of many calls in parallel, but I didn't do that this time. So this, for me, throwing this together in like a few minutes, I think the results actually were pretty interesting. Which was we measured fluency of the greedy decoded text, and the fluency of the greedy decoded text got a score of 5.3, which I think is not that bad. But the diversity was relatively low because basically all of them were the same. And then the diversity got higher and higher as we had more and more outputs, but the fluency went down. So this is a very common issue, which is like, as you sample more diverse things, the quality goes down. And temperature sampling is particularly well known for this. There's a lot of other methods that we're going to talk about next class that are kind of Pareto optimal with respect to diversity and quality. So you can get like better diversity and better quality. Better diversity and better quality than temperature sampling. Cool. Any questions here? Okay. One caveat I'd like to give about language models as judges is don't trust them blindly. Language models are very bad judges for a lot of things, and they're particularly bad at judging things where they themselves are not good at them. So if a language model is not good at solving math problems, it'll also generally be a bad judge for math problems. And another thing that people have reported is language model judges like their own generations more than they like other language models. So Claude will like really like Claude, GPT will really like GPT. This is not a hard and fast rule. It's not true all the time, but it is true some of the time. So be aware of that. Cool. So the final thing I'd like to talk about is meta generation algorithms. So this is going to be a big theme of the class, and this is the simplest possible meta generation algorithm again, which is re-ranking. And so what I want to do is I want to re-rank. I want to re-rank the output of GPT-2 small with GPT-2 medium. And so we have a bigger and stronger model, and then the smaller model that generates. So yeah, this is just the code to generate to calculate the probability. Actually, here this is the important code if you want to run on like a GPU or MPS, but hopefully like people have done this before. I'm sure like everybody's run on GPUs, but like if you're running just on your Mac, like definitely do this because this will speed it up by a lot for free. And like the smaller models you can actually run on your own computer. I'm getting an error. Why am I getting an error? Okay, maybe I just didn't run that. Cool. And so we can generate some outputs and calculate the log probabilities between them. So while we're waiting for this to finish, this is actually a commonly used method in inference where you use a small model to generate an output and then a larger model to like calculate the probability of the output. Does anyone know what the name for this is? It's not exactly what we're doing here yet. Speculative decoding, yes. So typically in speculative decoding, what you do is you use a small model to generate like 5 tokens or 10 tokens or whatever. And then you use the large model until you get to a point where the small model was wrong. And the reason why this is good is because like calculating tokens in batches is much faster on GPUs. So you can save a lot of time doing this, but we'll talk about that later also. So anyway, this is the output and the likelihood. So we have the future of artificial intelligence is bright and promising. The future of artificial intelligence is banana purple elephant, and artificial intelligence will transform many industries. And in this case, I guess the small model always gave a worse probability than the large one. So that's not like super exciting. But the more interesting thing is when we actually like use it for re-ranking. And so you get to see which outputs a particular model prefers. And in the case of a smaller model and a larger model from the same model family, it's actually pretty clear. It's pretty fun. So here's the small model. Here's the text that the small model prefers versus the text that the large model prefers. And because I generated from the small model, it will make a lot of sense that the small model will prefer most of these. So it's actually more interesting to look at the ones where the medium model prefers it. So let's look here. Okay. So actually there's only one. That's kind of boring. This is randomly sampled, so I get a different result every time. When I did it like earlier, I got 3, but here's the one. The future of artificial intelligence is shaping up in very interesting ways. In our next issue, we examine whether machine learning might be able to produce complex tasks. And here the medium model preferred it. Does anybody notice anything about the difference between that and this? Yeah, it's really long. Actually, unfortunately, I'm cutting these off here, so that's not it. Oh, I forgot to mention one other thing. So this is not the log probability. This is the per token log probability. And the reason why I did the per token log probability is that makes it easier to compare longer and shorter things on the same footing. Let me see if I can cut off this like stop this dot to dot stuff. Too many dots. Yes, I will. One second. Okay, here. And actually, let me generate again so we don't so we can get some like additional samples. But what I meant by the by which part?
No. That number is.
Oh, the per token log probability. So what we saw before when we generated from Quen on Tuesday was like the longer ones tended to have a high, like a lower probability. They had a larger absolute value of their log probability. And so like let's say we wanted to find the output where the medium model preferred it more than the small model by the largest margin. So like what and actually hopefully I can do that if we get more than one. Let me see if this works. Yeah, okay. So here what I did is I wanted to find the one where the medium model preferred it by the like most. And when I do this, I would like to have that be relatively independent of how long the actual output is. Because if the output is really long, the difference is going to be larger just because the magnitude, the overall magnitude is larger. And so by dividing by the number of tokens, we can like normalize for the length. Yeah, sequence level log probability normalized by length. Yeah. So here's a few more examples. So the future of artificial intelligence is now back on the forefront of technology. Believing AI will deny us an advantage over humans for modeling and understanding the human mind. It's a little bit weird. The future of artificial intelligence is at stake, he warned. Might there be a tipping point coming? But will championship golf can fulfill an American dream? Interesting. I kind of want to read this article, but so like, do people notice any difference between this and the ones that I had up here? Like still in its infancy, the full attention of expert scientific communities depends on an intelligent machines, driven both by the goals that saw the current scientific literature become obsolete and by priorities that reflect redistributive objectives for higher education. So maybe not as clear as I was hoping, but any ideas? No.
It seems like simple sentence.
Simpler sentences overall, yeah, maybe. What I would say is they have more surprising vocabulary, like more surprising vocabulary choices while still being mostly fluent. Like the golf kind of threw me for a loop, but and like my general overall impression of like stronger models, and larger models are typically stronger models, is that they give a higher probability or they're more likely to generate sentences that are kind of like interesting and surprising while still not being too like off the wall. And like just to give an example of this, I was trying to test whether DeepSeek or GPT-5 wrote better essays. And like I tried several of them, and DeepSeek would always write a great essay. It was just kind of like generic and boring. Whereas if I used GPT-5, it would write like an actually like somewhat interesting essay. And that's the level we're talking about with our strongest models now. And so, you know, the weaker models will like GPT-2 will not be at that level, but they still the same general trends hold. Like they're better at modeling low vocabulary items, low frequency, phenomena and other stuff like that. Cool. Yeah, that's all I had for today. Are there things that people would like to discuss around this? Yeah. Oh, what's the objective of what? Sorry, could you speak up? The downstream use case of meta generation is to improve quality, improve overall quality. So, let's give an example. Like you have a re-ranker that's a really strong model that you cannot generate, you cannot generate from efficiently. Let's say it's an agent that goes out to it's an agent that goes out and confirms information or something like that. So we'll also be talking about like tool use in the loop of generation and other stuff. If that's the case, you might not want to run that at generation time, but you might be willing to do that to confirm that there's no hallucinations in your text or something. And then do that over like 5 different texts. Another thing is self-consistency is also a variety of meta generation, where you generate multiple outputs and then you do majority voting over them. So like there's a lot of different varieties of this. Yeah. Cool. Any other things? Yeah.
Do you think the difference that you saw between DeepSeek and GPT-5 is mainly like on the training side or on the inference side?
The difference between DeepSeek and GPT-5, I think they're both reasoning models and I let them both reason. So I think it's probably more on the training side there. But yeah, GPT-5, we're not 100% sure what they're doing for inference. Yeah. Cool. Okay. Thanks everyone. Happy to do. Thanks. Did you? Oh, cool.